Good morning, class. How's everybody doing today? Hope you're all doing well. I know here in Canada we are currently we've experienced a bit of a cold snap. It is quite snappy out there. Very cold today, and you know, if you're in a warmer part of the world, just be thankful because, geez, cold is just, man. I'm about done with it at this point, you know? It's like, let's just get on with spring, shall we? Anyway. Hello to the 28 people who are currently in stream. We'll give people just a few moments to join the stream. Our numbers are still going up. I don't think we've plateaued just yet. But yes. Yes, indeed. If you want to see that, I suggest checking out the stream that I did the day that my game launched, where I played the game a bit and answered people's questions and talked to people, basically. Because there you will see me in a very silly hat. It is probably the silliest hat that I own. Which is saying something, because I do have a few silly hats. I mean, let's be honest, right? Nobody likes the cold. But you live in the cold because the real estate is too expensive everywhere else. That's why you're a Canadian, is because you have an aversion to expensive real estate. Although you can't really say that about the Canadian real estate market at the moment, for sure. Anyway, so let's get into yes, Canadians only live in Canada because they're the only people who are, you know, brave enough or stupid enough to be able to deal with Canadian winters. To be honest, though, I think Minnesota gets it a lot worse than Southern Ontario does. So the same thing applies twofold to Minnesota in the United States of America. But anyway. Unless you're living in Alberta, holy smoke. If there's anybody who's living, like, in the northern prairies, you don't even know what cold is. But anyway, we should talk about math and stuff. Yeah. So, anyway. Yeah, Southern Ontario is kind of like the Florida of Canada. Geographically and climatically. Anyway, so when we were last talking, we're talking about the recursion example for the Fibonacci sequence. So just to quickly recap, Fibonacci, any of you who have not seen the Dan Brown novel that came out reasonably recently, although I suppose that's like at least 10 years ago now that Dan Brown was popular. But anyway, the Fibonacci sequence is a sequence of numbers where every number is the sum of the two preceding numbers, right? So if you're at the base case of that sequence, then both the 0th and 1st element of the sequence, those are both 1. The Fibonacci numbers going up from there are the Fibonacci number of n minus 1 plus the Fibonacci number of n minus 2. Good. So, in general, we came up with an implementation of the Fibonacci sequence right here. We have a counter there that keeps track of how many iterations of the Fibonacci, how many recursive iterations is the wrong word. How many recursive calls to the Fibonacci function you make in order to calculate a particular number. And we were, of course, at only the Fibonacci number of 33, we were starting to hit, 4 or 7 million different recursive calls, which is because the number of recursive calls for this function blows up exponentially. Blows up is kind of a colloquialism in computer science. When the runtime increases in a very substantial manner with the size of the input, we colloquially refer to that as blowing up. So the runtime blew up at X point, right? It also kind of designates the point at which it's impractical to run the run the algorithm. But anyway, so this happens because each call to Fibonacci spawns 2 additional calls to Fibonacci, more or less. So you have a rough doubling of the number of recursive calls required in order to calculate any particular Fibonacci number. So, in general, the relationship is something like counter is going to be equal to 2 to the power of n, where n is the number that's being fed into the Fibonacci sequence, which is a bad runtime. So we were getting into how to measure that empirically. One way to measure it in practical terms, there is a very cool Linux function. Notice I had my stuff loaded ahead of time today, called time. So if you execute the time function, or just preface anything you run with the time function, what ends up happening is the computer calculates how long it takes for you to execute the given task. So you can see that when n is equal to 33, we end up with 2.3 seconds, which is fine. We could go higher than that, but you can see that's roughly in line with this chart here. So you can see by the time we're hitting n is equal to 40, our runtime in seconds is going to start hitting like 1.5 minutes, which obviously I'm not going to make you sit through during a lecture. But just keep in mind that, if you had, 41, it would be roughly 3 minutes, and 42 would be roughly 6 minutes. It would double like that. So there are a couple of problems. Fly or something. There are a couple of problems with estimating your runtime in this particular fashion. Most particularly, the runtime that you get for, n is equal to 35, for example, that's going to be highly dependent on the particular computer system that you are running it on, right? The clock speed of the CPU, the amount of memory available, all of these things have an impact on the runtime. So it is very important that while these numbers give you an idea of the growth of the runtime with respect to n, they do not, these are not to be relied upon as exact figures. Basically, the problem with computers is that it's almost impossible to create laboratory conditions with the computer, right? Computers change too rapidly. There are too many different types of computers. It's not, in practical terms, it would be impossible to come up with a runtime for some program that's applicable to all computers. It just can't happen, right? Contrast that with the physical sciences, where, the speed of light is the speed of light, no matter how no matter who is measuring it. These values will change substantively depending on who's measuring it and with what. So, what's important here is not the raw runtime numbers themselves. A really good computer might be able to do 50, in the amount of time it takes this one to do 35. The trick is, what the important part of this is the relation between n and the number of seconds, because that that relationship, the manner in which the runtime is doubling with each additional every incremented value of n, that relation is going to be highly stable across the different platforms on which you might test this algorithm. And that's why we use things like big O notation. That's why when we talk about the runtime of algorithms, and we're comparing runtimes of algorithms, generally speaking, we use mathematical formulae rather than raw runtime values, because they're kind of meaningless when it comes to computers. So, yeah, exponential function increases quickly the larger that n gets, obviously. You'd have, in order to get a really good idea of how this works, you'd have to plot it on a logarithmic chart. So, let me see if we've got any... Yeah. Yeah, one of the things that I recommend to people who are from other parts of the world and have to deal with Canadian winters, like international students who've come to the university for and are in Canada for the first time, I'm like, buy a coat that's at least twice as thick as you think you need. You'll thank yourself later. What's the best way to practice for the midterm? Do the assignment material. The coding bat questions are still applicable. I'm just going to tell you right now, the midterm is going to be focusing primarily on the data structures stuff. So practice your data structures. Uh-oh. Uh-oh. Did I lose both? Hello? Oh, okay, so I'm still getting... Okay. Still... Okay, I don't have to repeat myself, but I lost the camera. Yet another funny face for your prof to get stuck on. Hilarious. Let's see if this works. Flip it back. Flip it forward. There we go. Okay. And audio. Yep. I wish this wasn't like this. So annoying. Nope, that's still not it. Yeah, okay. There we go. All right, cool. Well, at least it doesn't break catastrophically anymore. Last time, I would be last semester before I got my internet fixed, I would go on for a full 3 minutes before realizing that the stream had just cut. So this is a better situation because at least the slides are still coming through, but I don't know. I'm gonna chalk it up to Linux problems. So anyway, so the question then becomes: if this algorithm is so bad, how might it be improved? And we're going to improve this algorithm through a process called memoization. That is, the process of creating memos. We are going to integrate the idea of keeping memos into this algorithm. So, the idea is, during the recursion, during all of the recursive calls, we keep a pool of memory common to all of the recursive calls that are executing. So all of these recursive calls are going to be referring to one dictionary. Inside of that dictionary, we're going to keep track of all of the values that are being calculated. And instead of invoking a recursive call, if the value that we want is in the dictionary, we just pull it from the dictionary. There is that fly. Stupid little fly. Get out of here. I was going to kill it, but then it was like, I'm just going to knock over my camera when I do that. Anyway, so the idea is we want to try to avoid recursion when we can. Most particularly, we want to try to avoid instances of the recursion branching into double branches. So let's try to do that. I'm just going to copy this dude. There we go. And we shall call that fib memo. There we go. So we're still going to, let's keep the counter in there just to be able to see how many times this guy is called, to see if it's actually working. So we want to leave the base case alone, because the base case is not the one that's contributing anything to the runtime, right? There are no recursive calls being made inside of the base case. It's just returning a straight constant value, which is super fast and super easy. So that we don't have to worry about. This is the guy we have to worry about. So rather than having both of these recursive calls occur in the same line, let's space them out a little bit so that we can work on them. So we'll call these F1 and F2. F1 is equal to fib memo n-1, and F2 is equal to fib memo n-2. Cool. So let's take a look at these. So what we want to do is we want to keep a memo, right? So you can do this one of two ways. You can either make the memo a global variable, or you can make it an argument to the function. Generally speaking, we like to avoid global variables whenever possible. So let's make it an argument to the function. Memo is now an argument to the function. And let's go one step further and give it a default value. This way, if we give it a default value, then we don't have to specify a blank dictionary down here. It will, if it's called without a memo specified, then it'll just automatically insert a blank dictionary if we make the default a blank dictionary. And so long as we make sure that all of our calls to fib memo inside of the function provide an argument for the dictionary, provide something for that dictionary argument, we don't have to worry about it resetting to a blank dictionary each time, right? Let me see if people have questions so far. Memoization sounds like a 2-year-old saying memorization. Yes, it does. But, memoization and memorization, you can actually kind of think of them like they're kind of the same thing, in this context. It's like rather than having to recalculate everything out, you're having the computer basically memorize its timetables. Times tables. So the whole thing about this is we want, before we perform this, before we step into this recursion, what we want to do is we want to see if the value we're looking for exists in the dictionary. So if memo at n-1, or no, you want to do it differently. If n-1 is in memo.keys, or you don't even have to do .keys, because the in operator automatically searches the keys of a dictionary, so this should work just the way it is. Then we do something, and if it's not, then we invoke the recursion. Cool. So if it's not in the dictionary, we wish to put it into the dictionary. So memo at n-1, because remember, you can add something to a dictionary simply using an assignment operator, is equal to sorry. I mixed myself up. The else case is when it's not in the dictionary. If it's in the dictionary, then we just want to pull it out of the dictionary. Memo at n-1. F1 is equal to memo at n-1, right? That makes sense. We're taking a value for f1 directly from the dictionary, right? So if n-1 is not in the memo, that's the else case, then we want to put it in there. So there we go. Memo at n-1 is equal to fib memo at n-1. So the result of the recursive call is stored in the dictionary. We can then assign to f1 this guy. And for those of you who are you have your optimizing eyes on, you know that if you have a statement that appears at the beginning of two branches of an if statement, all you have to do is pull it out and put it afterwards, right? And you might also note that this construction is kind of dumb. You don't need to put the else case. All you have to do is say n1 not in memo. So if n-1 is not in the memo, then memo at n-1 is equal to fib memo n-1. Then afterwards, f1 is equal to the value that has been just recently stored in the memo if it wasn't there. Cool. And then all we have to do is copy and paste for f2, and that's all you need. Cool. So let's save that up and see how many executions, how many recursive calls we now get. Oh. What order is this being printed in? Okay, so the counter is the second one. So, is that really the Fibonacci number? That's crazy. What about, let's do something smaller so I can actually tell if it's correct. Yeah, okay. So, the Fibonacci sequence is 1, 1, 2, 3, 5, 8. So since we're using 0 indexing here, the fifth element, or element number 5, which is the sixth element, is 8, so that checks out. And notice that under the previous iteration, we would have had 15 calls, recursive calls. In this case, we have 8. So if we do something like 33, we have shaved our number of recursive calls down to 306 from 11 million. So you can see, the bigger the thing gets, the more the savings are, right? You know, going from 15 to 12 doesn't seem like a big deal, but going from 11 million to 300, that does seem like a big deal. So let me see here. Yeah, let's pick this apart just a little bit, see what's going on under the hood. So, print n is equal to, and then n, and print memo is equal to, and then memo. I think this will work. Hopefully this works. I have to invoke the right fib. No. There we go. Yeah, cool. So, starting at the top, we note, I think I've made a, oh yeah, I made an error, didn't I? There we go. We should be able to shave that down even further. Yeah, I thought that was too much. Yeah, okay. So, and we're gonna have to move this guy somewhere more useful. Let's move it to immediately before we calculate our return value. Cool. All right. So, yeah, now we can actually see stuff. So, the first invocation is at 33, right? So we start and we have to calculate 33. We go through, and then we hit this guy, right? Because the dictionary is empty, so you're going to hit this statement, right? So that requires n at, or that requires the Fibonacci, the 32nd Fibonacci number. That requires the 31st, the 30th, the 29th, etc., 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 all the way down until we hit the base cases. Once we hit a base case of 1, we can start, building up the dictionary, because at each one of these points, if we're trying to find the value of n at 2, you'll notice that while we may have stopped here, this one is going to be calculated, right? By the time we hit this one, all of these guys are going to have to be calculated. Because remember, this calling of the function must be completely resolved before we hit all of the F2s, right? So basically, this has reduced the number of recursive calls that must occur, but we've reduced it from 2 to the power of n to n, right? Which is very, very, very good. The price that we pay, though, for this is memory, right? We're now keeping track of all kinds of intermediate values in memory that we didn't have to before. You could make the argument that all of the successive recursive calls have to be stored in memory somewhere. So really, this would be more memory efficient as well. But, there's certainly a lot more declared memory in this iteration of it than there was previously. But you notice that we went from like 2 seconds to 55 seconds for the amount of time that we needed to calculate this, which means that we can go up to like really big numbers now, right? I'm just going to stop printing those because that's just going to fill my screen with lots of stuff. But yeah, so whereas before we were sort of tapping out around 30, we can now calculate Fibonacci numbers that are way higher than that. Yeah, so we're literally now hitting our recursion limit, which wasn't the problem that we were having before. So yeah, that's memoization. Any questions? Oh, yeah, okay. So the slides make one more sort of optimization that I didn't. You don't actually need F1 or F2 at all. You can just put these guys directly in there and save that memory, which is pretty cool. Oh, and one other thing while we're here. What happens if you flip these around? It's kind of cool. This should give you like, let me just reinstate the print statements. This should indicate to you that although things look like they are, although things look like they're happening all at once, in fact, it is still proceeding linearly, right? And you can see that because the dictionary's kind of, well, it's being ordered according to its... But yeah, you can see that if we put the n-2 case up front, then it's always calculating the value that's 2 underneath the currently calculating Fibonacci number. So the cases, the calls that it moves into are 30, 28, 26, 24, etc. On down the line, it's counting down by 2s. So it's skipping an element, which means that we have to calculate out the ones that we're missing, pardon me, periodically as we bump ourselves up back through the hierarchy of function calls. So yeah. Nobody seems to have any questions, which means either I'm perfect at explaining things or you guys aren't paying attention. I'm just kidding. I'm sure you're all paying attention. But yeah, cool. So as you can see, our relation now between n and the number of seconds it takes to calculate something, you can see that we are, roughly speaking, increasing, this looks like a linear relationship rather than an exponential relationship, right? So, yes, runtime scales linearly with n. This means that this algorithm is efficient even for very large values of n, which is good. Generally speaking, this is what separates a good algorithm from a bad algorithm. In fact, just for a little bit of computer science nomenclature, we would consider the basic implementation of Fibonacci here, we call this a brute force solution. A brute force solution in computer science, generally speaking, is an algorithm which is it is a simple algorithm that relies on the speed and raw power of the computer system it is operating on to be able to handle larger problems. That's a brute force solution. An efficient or optimized solution is one that uses clever algorithmic tricks in order to not be quite so reliant on raw computing power to solve problems. This is an optimized solution. The previous was a brute force solution. So cool. That's all that. Paying attention, just tired. Okay. Is memoization like adding calculated fib numbers into a dictionary, then checking to see if they exist in the dictionary? Yes! That is a perfect one-sentence summary of what memoization is. Yes, cool. Yeah, okay. I get it. It's well, no! Last week was midterm week. You guys don't have any excuse this week. Unless it's my midterm that's making you tired. I guess. So, moving right along. Let's talk about searching. So, in the last example, in the last section, we got into what I would consider to be more highly algorithmic type talk. We're talking about analysis of algorithms. We're talking about runtime of algorithms. These are the types of topics that you will see if you ever take a data structures and algorithms course. Now, interesting thing about data structures and algorithms, it turns out that there's a reason that they group those two ideas together, because very often the data structure is the algorithm, but that's, at any rate. So let's talk about another very, very, very typical data structures and algorithms type topic, which is searching. This is classic algorithms material. It's like searching and sorting. Those are the two classic topics, like introductory topics in any algorithms course. Any algorithms course worth its salt, anyway. So what is a search? How do we define a search algorithm? So, suppose that we have a sequence of items of a certain length n, and we want to know if a particular element is in the sequence of items. These items might be integers, they might be objects, they might be strings, they might be anything, any basic, they might be other collections. Basically, think of it, if you need a concrete mental model, think of a list or a tuple, right? Basic ordered data structure. How many entries of the sequence do we have to check in order to find out if it is or isn't in the list? So let's think about that for a second. So we have a list. It has a bunch of random values in it. How many of those values do we have to check to see if one particular value is in or is not in that list? All of them, until you've found it, right? So that's sort of the that's your worst case scenario, right? However, if the list has some degree of organization, we can do a lot better than just we have to search each element in the list, right? So, generally speaking, when we say organized, what we mean is sorted, right? So, sorted means it goes from the smallest element up to the biggest element. So, unstructured search is the type of search that we were talking about, where we can't assume anything about the list. You have to go through each element in sequence, find out if it is equal to the target element, and if so, return true or false. Unstructured search looks like this. I won't bother implementing it for you because it's pretty basic. Def search 1, looking at listed element for I in range, for every I, for every index in the list, L at I, if L at I is equal to E, return true, and if you never return true, return false. Unstructured search. This is sometimes called linear search because it goes through the sequence in a linear fashion, and its runtime is a linear function of the list size. So it's big O of n, for those of you who know big O notation. So, if you want to search a sorted list, you can make a few assumptions that make this job much easier. So, we are going to describe an algorithm here known as binary search. So, let's take this list and assume that it's in increasing order. Take a look at the middle element of that list, like dead center, or slightly off center if it's an even number of things in it. If that value is less than the target value that you're looking for, you know that the value you're looking for can't be any way. It can't be. I have to flip myself. It can't be in the side of the list that contains values less than the element that's less than the element you're looking for, right? So imagine the list bisected into two segments, right? All of the values in the lower segment are less than the middle value. All of the values in the higher segment are greater than the middle value. If the middle value is less than the element you're looking for, you know the element you're looking for has to be in the sector with the elements that are bigger than the middle value. So that means you can exclude from the search everything that's in the lesser segment, right? Or sector. So you can then perform the same searching operation on just that larger segment, right? So you have effectively, if you continue to do that, you eliminate half of the possible locations for the element you're searching for at each step, half of the remaining elements. So let's see if we can, implement that. So, def bin search. We are looking through list L for element E. So, 4. No, not 4. We want to, first we need to pick out what the middle value is, right? So, the middle value is going to be L at length of L integer divide by 2, right? So the length of L is n divided by 2 is, you know, close enough to the middle for this to work. So, if L at the midpoint is greater than E, then we know that that the element we're looking for must be in the lesser half, right? So we can, well, actually, let me do out the rest of this if statement first. So if L at mid is less than E, and then we also want to deal with the case where L at mid is equal to E, which is caught automatically by the else case. If that is the case, if L at mid is E, then we just return true. Right? Because we've found it. Well, actually, we do need to do some more. You know what? Let's just leave that for the moment. I'm gonna sneeze. Pardon me. So, we can actually call the binary search algorithm recursively on the sublist. So, if we have, you know, an ordered list 1, 2, 3, 4, 5, 6, 7, and the middle value is 4, and we're looking for 6, which, no, sorry. In the first case, it would be the middle value is 4, and we're looking for 2. So 4 being greater than 2 means that this is the segment that we need to look for, right? So we'll perform binary search on a slice of the list from the beginning of the list to the midpoint. Remember that a list slice actually takes 1 minus this value, right? So this will give us this list right here. Conversely, if we're looking for the top half, bin search L from mid plus 1, because remember, we want to get from here to there, to the end of the list. And of course, both of these we need to pass the element that we're looking for. So, we'll add something to the top here. If L at mid is equal to E, then we want to return true. That will be our we've found it condition. If if length of L is equal to 0, or if length of L is equal to 1, and L at 0, because there's only one element in it, is not equal to E, then that's our failure condition. The search has failed. All right? So let's see if this works. Bin search. I'm just going to do a list conversion on a range to 50. For 34. Let's see if that works. Print that dude there. List index out of range. have to do a little bit of sleuthing here. Cool. So mid is 38? What? That don't make no sense. So we do hit the top half, right? Mid is... Oh, so it's saying this one, which is like the correct middle value. Oh! Yeah, okay. Throughout this algorithm, I'm using mid as like the index. I'm using it as an index, but up here I'm just using it as a value. That was my error. Yeah, so there we go. Oh, and so I've messed up my base case a little bit. So the mid value here is 1. Which is the value that we're looking for. So, so why wouldn't it get caught there? Chat's probably going nuts right there. You still have midterms this week? Oof. Oof. Thank you, guys. So, let's see. So L at mid is 34. So why wouldn't this execute? Doesn't make any sense. It does. So it does return true. Oh! I got it. If you don't okay, so that's actually a really good... I'm really glad I hit that error because that's a common pitfall with recursive algorithms. So it's not sufficient to just perform to invoke the recursive call. You have to make sure that whatever return value you need to return is being passed back up through the chain of calls so that it reaches the top level function call. Save that, execute it, there we go. Now we get true. There we go. Excellent. And you notice how I just printed an exclamation mark in that branch there? That's a little trick that I perform when I want to see if a branch is executing. I just, print some little character to see if that character prints, to see if that branch, like if I'm not sure if I want to check the condition to see if a condition is actually working out. So the other thing that you want to do is you want to test a negative test. So let's see if 80 is in that. List index out of range. I'm just going to modify this. Well, Well, I'm actually gonna take a look at what the slides implementation is. Yeah. Okay. So basically, doesn't seem that different. Anyway, there's some problem in there. But anyway, here is a visualization of the process happening on a list with more random numbers, right? So we've got the full list. The middle value is 22. Assuming we're searching for 33, that means we sort of bisect the list in half using the top half. We then 33 is less than the middle value of that, so we go down, and then we go up, and there you go. That's how binary search works. So, yes. Binary search using recursion is much faster because it only has to look at a small number of items in the list to find the one it's looking for. If the list has a length n, then the binary search algorithm using recursion looks at approximately, or possibly at most like a couple, maybe extra, log base 2 n elements of the list. So, whereas in the unmemoized Fibonacci, we had an exponential growth, and we turned it into linear, we're now taking linear and turning it into logarithmic, which is much better at large values. So this is, again, a very efficient algorithm. So that is class. I'm gonna answer some questions, but I'm gonna be right back. Just put your questions in the chat. So, a couple of questions, both related to the degree to which recursion and memoization is going to be on the test. Recursion is definitely going to be on the test. Again, the test content kind of focuses a little bit more on the data structures material, so it's like it's not going to be the primary. It's not like the entire test is going to be on recursion, you know. I wouldn't even say that 50% of the test is going to be on recursion. And will you be required to know memoization on the test? Put me on the spot, why don't you? No. I'll just say it. I'm nice. I'll tell you. Yeah. There's no memoization question on the test. This time! I'm not saying there won't be on the exam. But it just so happens that for this particular test, The answer is no. Can I be heard? Oh, yeah, there we go. Will you be marked on how efficient your code is? No. No. As usual, your code will be marked purely on whether it works. Now, if your code is so inefficient that it cannot be executed on our servers, that does mean that you will lose some marks. But if you can run it, then we can run it. And if we can run it, then we will be, we'll be evaluating it on the basis that we have always evaluated your code, and will always evaluate your code. Black box testing. Does it produce the correct outputs for specific inputs? Now, every once in a while in this course, we may say that a particular recursive algorithm or something like that must execute in, X number of recursive steps for, we might specify how many recursive steps your algorithm should take for a particular problem, because that's actually going to be a constant value if you've implemented the algorithm correctly. Or at the very least, it should only be off by 2 or 3 recursive invocations. So that kind of thing, that's totally testable, right? But to some degree, that's still black box testing. It's just kind of better integrated with the sort of meta properties of your algorithm. So yeah, I believe there's a question on one of the assignments that's you must, there's a memoization question on one of the assignments. It might be A5, and it's A5 or A6, I'm not sure, but it's it gives you some test cases that won't execute unless you have unless you've gotten to gotten the memoization correct, right? In the same way that the Fibonacci numbers won't, you just practically can't run 200 of them using non-memoized. So yeah, that sort of thing. It's we sort of eat around the cookie with respect to optimization. But no, in general, we're still providing you the leeway to make mistakes with respect to optimization, because the fundamental thing is that you learn how to produce the correct output. It doesn't matter how efficient your code is if it doesn't produce the correct output. Yeah. Any other questions? Yeah. It's also it doesn't matter whether your code would produce the correct output if it doesn't compile, right? There's a hierarchy of problematic things in code, right? The most problematic thing in code is your code not compiling. The second most problematic thing is the code not producing the correct output. The third most problematic thing in code is your code having running into runtime errors sometimes, right? For some specific test cases, it'll just flop out and die. That's a problem, but it's less of a problem than you cannot produce the correct output. And then your code runs inefficiently is underneath that even. So we have to pick the level at which we're docking marks for things. And generally, it's those top 3 levels. Again, if it's so poorly optimized that it doesn't run at all, that's usually pretty easy to pick up. Okay. Well, let me see if I have any questions that have been blocked by... There we go. All right. So, I guess I'll let you go. Thank you very much for listening to me gabbing on about nonsense for an hour. Have fun. Good luck on those midterms, including the bio midterm of Ultimate Peril. We'll talk again on Thursday.